In this lesson, we're going to look at the difference between even and odd functions, which we'll focus on graphically, but we'll also look at algebraic tests to see how you can verify if a function is even or odd. Then we'll end the video with a couple examples, both graphical and algebraic. So really simply, a function is even if it reflects across the y-axis. So if you graph an absolute value function, that's actually a perfect example of an even function, because it reflects perfectly across the y-axis. Another example of an even function would be y equals x squared. But we can say a little bit more than just it reflects across the y-axis. So let's look a little bit more specifically, like with this parabola example. If I look at positive x values, that means I'm going to the right. I end up with these positive y values. If I look at the negative x values going to the left, I end up with the same y values. So you could say if you plug in positive and negative x values and you get the same output values, that's an even function. If we skip ahead in the notes a little bit, that's what this is showing me here. If you plug in negative x values and positive x values, you get the same output. We're saying that these outputs are equal to each other. Now let's contrast that with an odd function. We say a function is odd if it rotates about the origin. A great example of that is the function x cubed. Again, if we wanted to be a little bit more specific about this, we could say that if we plug in positive x values, we get these, well, I guess positive y values. Whereas if we plug in these negative x values, we get the exact opposite y values. They end up being the same value, but negative. In other words, you could say plugging in opposite x values gives you opposite outputs. Jumping ahead a little bit in the notes, we can see for an odd function, we're plugging in a negative x and we're plugging in a positive x, but look what happens for the outputs. Here we get a positive output, here we get a negative output. It doesn't really matter what side is positive and what side is negative. The important part is just that these are opposite values of each other. So let's test out this algebraic idea. I'm going to start by plugging in negative x into the function g of x. So that would look like, well, negative x squared plus 6. And this is really like negative 1 times x squared. And you can distribute an exponent across multiplication. So that's like negative 1 squared, which is just 1 and then x squared plus 6. So that's just x squared plus 6. Well, that's the same as the original function g of x. That means I can say g of negative x equals g of x. Or in other words, when I plug in positive and negative inputs, I get the same output. That tells me this is an even function. Let's do the same thing for the next example. So I'll look at h of negative x, which would be 3 times negative x to the 5/2 power. And if you don't like this fractional exponent, remember you could write it in radical form just by putting this denominator as the radical. So this would be 3 times the square root, or the second root, of negative x to the 5th power. Now, when you take a negative thing to the 5th power to an odd power, it stays negative. So this would still be 3 times the square root of negative x to the 5th. I can simplify it that way. Now, this is not the same as the original function, so that means it's not even. But it could be neither, so just because it's not even doesn't mean that it has to be odd. So now I have to look at negative h of x and see what happens here. If I just take the original function and multiply it by a negative 1 in front, that would look like this. And again, I could write it in radical form, but the negative 3 still stays out front, so this would be the square root of x to the 5th here, but it would be negative 3 in front. Now these are also not the same thing. In other words, h of negative x, the first thing I found, that's also not the same thing as negative h of x. So that means it's also not odd. And if something is not even and not odd, that means it must be neither. Alright, so let's do another one. For j of x, I'll start by plugging in negative x and see what happens. So this is the square root of 4 minus, and then in parentheses, negative x, which is being squared. If you square a negative thing, it makes it positive, so this is the square root of 4 minus, and then just positive x squared. And that is the same as the original function, so that means this is an even function. If you remember from some previous practice, this is actually the equation of part of a circle. It's just the positive square root, which means it's just the top side of the circle, but that makes sense why it's an even function then, because it would reflect exactly on the left and the right side. Alright, now let's look at k of x. Again, I'll start by looking at k of negative x, which would be negative x in parentheses cubed, minus, and then again negative x in parentheses squared. Now cubing a negative keeps it negative, so negative x cubed, but here squaring a negative makes it positive, so minus from here, but then positive x squared. Now this is not the same as the original, which means it's not even. Since if I look at k of negative x and k of x, these are not the same, that means it's not even. Now I have to look at negative k of x. That would be like taking the function x cubed minus x squared and just multiplying it by negative 1. And if you distribute that negative in, that gives you negative x cubed plus x squared. So I could also write k of negative x also doesn't equal negative k of x. Since none of these things are matching up, it's not even, it's also not odd, that means it must be neither. So far we've gotten two functions that were even and two functions that were neither. We can also figure out if some more complicated trigonometric functions are even or odd just by looking at their graphs. So for instance, sine of x is rotating about the origin, so this is an odd function. I can also see how tangent here is rotating about the origin. Even this bottom right part ends up being the top left part. So that's also odd. Same thing for cosecant, which is in the top right and the bottom left. And it might be a little bit tougher to see, but cotangent is also rotating about the origin, which means all of those are odd. But then cosine, which is reflecting perfectly across the y-axis, and secant, which is also reflecting perfectly across the y-axis, those are both even. So it's okay if you're not familiar with these functions. We'll see them a lot more later in the class. But for now, we just wanted to use these as some interesting examples of graphs that we could figure out if they were even or odd. Here are some more functions that we can use to test if they're even or odd algebraically. You should pause the video and try these on your own, and then I'll put all the answers up and you can check your answers with mine. So here's what I got. I found 3 even examples and 2 examples that were neither even nor odd. Again, feel free to pause the video and look back at your work, checking it against mine. The last bit of this lesson is an example where it gives us part of the function drawn already, and we have to complete the rest of the graph just knowing whether it's even or odd. So in this first even example, we have the right side of the graph, and if it's even, I know that the left side of the graph is going to be exactly the same because everything is just going to reflect across the y-axis. So here there's the point 1, 1, that'll become the point negative 1, 1. Here I have the point 2, 1, that'll become negative 2, 1. So I know it's basically going to look like that. It's a little bit off, but as long as it looks basically the same on the left and the right, we're good. Then for the next example, it says we have an odd function and it wants us to draw the right side. It's in the bottom left quadrant. That means I have to rotate it about the origin, meaning it's going to end up in the top right quadrant. So this point negative 2, negative 1, that'll become the point 2, 1. Here, the point negative 1, negative 2, that'll become the point 1, 2. You can see how everything is rotating 180 degrees. So this graph will be up here. And if you rotate your paper 180 degrees, you can see that what they drew in the bottom left quadrant does end up exactly where we drew this in the top right quadrant. So then it says find the y value when x equals 2. Well, when x equals 2, that's over here, and the y value is 1. And then when it says to compare them, well, f of 2, we just found that was 1. And f of negative 2, if we look at the left side of the graph, that's the same thing as on the right, so the y value is also 1. Since these are the same, that verifies that this is even. Since f of some x value and f of the opposite x value gives me the same output, that verifies that this is an even function. For the odd example though, if I look at the y value when x equals 2, that's right here, so the y value is 1. So f of 2 equals 1, and if I look at the other side, f of negative 2, that's on the left side of the graph, that's here where y equals negative 1. Since when I plug in opposite x values, I end up with opposite y values, that verifies that this thing is an odd